Hi, so in this video, I wanted to take a look at some of the common equilibria that we'll see throughout this chapter regarding acids and bases, and then we'll also dive into kind of how we represent just how acidic or basic a substance is using the pH scale. All right, so to get us started, I wanted us to take a look at this reaction that I have written out here. This is a acid dissociation equilibrium for just like a generic acid, which we'll call HA. This is a Bronsted-Lowry acid, right? It has a proton at the front of it, so it looks very recognizable as an acid. But when that acid reacts with water, we produce then A minus, its conjugate base, and then H3O plus or hydronium as well. This is written out really generically so that whatever the acid contains, right, it has like a hydrogen at the front of it, and then it has something else, some anion. The anion itself is not necessarily all that important, right? So we just write it here as a placeholder like A or A minus, right, to represent that minus charge that goes with the proton itself. But so for this reaction that I have written out right here, consider what the equilibrium constant of concentrations would look like for a reaction like this one. So maybe pause, think about how you would write out the Kc expression for this reaction in terms of concentration, and then we'll show it in just a moment. So when writing out the Kc expression for this, it's going to follow the same rules that we looked at in the equilibrium chapter, basically just taking the products over the reactants and putting them to whatever power their molar coefficient is. In this case, all of our molar coefficients are 1. The only thing to note, right, is that because we have liquid water in this reaction, pure liquids and pure solids do not appear in our equilibrium constants, and so basically we can ignore that from there. But so what that leaves us with then is an equilibrium constant like this one, where we have the concentration of the conjugate base times the concentration of hydronium divided by the concentration of the acid. Now here I've labeled this as Ka rather than Kc. This is known as the acid dissociation constant. So it's just a specific equilibrium constant applied to a specific type of reaction. When we have an acid dissociation reaction like this one, right, it has some associated Ka value to it. In the same way, we can consider a base dissociation equilibrium and its constant. So if I have just like a generic base, again, following the Bronsted-Lowry definition, that base is going to accept a proton. And so we can imagine how that base would interact with water to take a proton away from the water, leaving us then with the conjugate acid of the base, which we'll call BH+. And then the remaining part of the water is just a hydroxide ion, so OH minus. Now this has then an equilibrium constant written out like so as the concentration of the conjugate acid times the concentration of hydroxide divided by the concentration of the base itself. This similarly is known as the base dissociation constant, or more realistically like the base ionization constant. Bronsted-Lowry bases don't actually necessarily dissociate, right? They don't separate, they just take on more atoms. And so that's why, realistically, this is more of just like an ionization rather than a dissociation or a separation. But it works in the exact same way, right? It's again just the products over the reactants for a base dissociation reaction, which again, we have like a generic format of that up above. Now I want us to kind of consider what this means for our different types of acids and bases. We reviewed in class like strong acids, and then also there are strong bases, but right, we also have weak versions of those as well. So like a weak acid or a weak base is something that will only partially dissociate or partially ionize. And so knowing that, right, the fact that it doesn't completely separate or completely dissociate, what would that then imply about, say, the relative size of this K constant? So in this case, if I have my Kb that I have written up above, if that Kb applies to a weak base specifically, does that mean that Kb is going to be rather large or rather small? You can go ahead and pause and think about this, and then we'll discuss. So if we have some kind of weak base dissociation, what that means is that the concentration of, say, the conjugate acid and the concentration of hydroxide, that's going to be relatively small, right? Because it only partially dissociates, we only get a little bit of those products out. And so if we have very few products and a lot more reactants, then that means that Kb itself is going to be a smaller value. How the trend goes is that if you have, say, a weaker base, that's going to have a smaller Kb value. Likewise, if you have a weaker acid, that will have a smaller Ka value. For strong acids or strong bases, those will completely dissociate. And so that implies then that its associated K constant is relatively large. In fact, like we could just say infinite. So when nitric acid dissociates, according to that acid dissociation equilibrium, really this isn't much of an equilibrium at all, right? Because this is a complete dissociation, this is truly just like a straight forward reaction. And so the equilibrium constant for this reaction would not even necessarily be given, right? It's just assumed to be essentially infinity, where all of our HNO3 separates into NO3 minus and then H plus, or if we have it bonded to a water molecule, we make then H3O plus. Now, in this equilibrium, we still define nitrate as, say, the conjugate base of our acid, nitric acid, but that nitrate is not necessarily like a super effective conjugate base. What I mean by that is like, the idea is that this base that's produced here could in fact react with water to then form its conjugate acid and some hydroxide. But because this initial acid dissociation is completely forward, the reverse reaction essentially like won't be able to happen at all. And I know that these are not perfect reverses of one another, but it's a similar idea of the nitrate turning back into the nitric acid, right? It's not really going to occur that way because that forward reaction was so strong. And so what that essentially means is that the conjugate base of a strong acid is going to have a Kb that is effectively zero. It cannot really ionize in the way that a base would because that forward reaction of dissociating into the conjugate base was so strong, right? That's going to mean then that the Kb is going to be very small, so very weak base. So the relative strength of an acid and its conjugate base are inversely related, right? That's to say that if I have like a strong acid, it has a weak conjugate base, or for like a weaker acid, it will have then a stronger conjugate base, right? So the relationship kind of works as like a seesaw where one increases, the other decreases. And the same goes for, say, like a weak base will have a stronger conjugate acid and vice versa. Now, something that I want to consider next is kind of how acids and bases interact with each other. So specifically here, I have like a neutralization occurring between hydronium and hydroxide. Right? If I have an acid, it will make hydronium. If I have a base, it makes hydroxide. And so when I mix those two things together, what results is then just some liquid water, as shown in this equilibrium right here. Now, I've written out the K constant for this reaction as just 1 times 10 to the 14. So that means that this is very much favoring the product side. So when I mix together hydronium and hydroxide, I get a lot of water and very few reactants kind of left over from that. Now we can imagine right here kind of the reverse reaction, where instead I have water molecules dissociating into H3O plus and OH minus. Remember that water itself is amphiprotic, meaning that it can act as both an acid and a base. And so in the same way, right, we can use water to make H3O plus like an acid would, or to make hydroxide like a base would. Now for this reverse reaction that I have written out right here, what would be the equilibrium constant for that? Or if we know this forward reaction has a K constant of 1 times 10 to the 14, what would be then the equilibrium constant of the reverse scenario? So recall that when we manipulate an equilibrium, right, we can say multiply a reaction by a factor, or we can reverse it, flip it around. In this case, when we reverse a reaction, what we're going to do is take the inverse of its equilibrium constant. So if the original equation was 1 times 10 to the 14, our new reaction is going to have a K constant that is 1 divided by 1 times 10 to the 14, or in essence, 1 times 10 to the minus 14. Now this is referred to as Kw, or the ion product constant for water, also known as the autoionization constant for water. Autoionization just means like self-ionizing. So this will occur when we have like two water molecules reacting with one another. One is going to ionize in the positive direction, one ionizes in the negative direction, leaving us then with hydronium and OH minus. And so this at 25 degrees Celsius has a K constant of 1.0 times 10 to the minus 14. Now again, this is just like another equilibrium constant. It is the expression of the products over the reactants. And in this case, our products are H3O plus and OH minus. Our reactant is just liquid water, but because pure liquids don't appear in the equilibrium constant expression, right, our Kw is basically equal to the concentration of hydronium times the concentration of OH minus. Now, this idea of the autoionization of water is really interesting because it kind of tells us that even pure water is not necessarily pure H2O, right? Whenever you have two water molecules coming into contact with each other like this, there is a chance that they will ionize. And so that means if I have a sample of pure water, it's going to have a lot of water in it, but it's also going to have very small amounts of hydronium and hydroxide, even if it is technically just water. Now, with this Kw constant, we can see that hydronium and hydroxide are kind of inversely related in terms of concentration. Because the product of those two concentrations is equal to a constant, as the hydronium concentration increases, the hydroxide concentration must decrease. But always both are going to be present, not just in, say, like water, but in really any aqueous solution, right? When water is around, it will have these two ions as well. Now again, because these concentrations are inversely related, what we see is that for acidic solutions, they may have just like a higher concentration of H3O plus and then a lower concentration of OH minus. In the same way, a basic solution is going to have more hydroxide than it does hydronium, but again, both are present at all times. So here I want us to use the Kw constant to relate these two concentrations. Say I have a solution that has a hydronium concentration of 2.6 times 10 to the minus 9. What would be then the concentration of the hydroxide in this solution? Go ahead and pause, solve for this, and then we'll compare answers. All right, so solving for this one, right, I'm going to use my Kw expression up above and the Kw constant. I know the concentration of H3O plus as 2.6 times 10 to the minus 9, and so that times the concentration of OH minus is going to be equal to 1.0 times 10 to the minus 14. So solving for that, I find that the concentration of hydroxide is equal to 3.8 times 10 to the minus 6 molar. Now this is a good reminder to, especially when you are using our little scientific calculator, to always double check your math when you are, say, like dividing by something with scientific notation. It's very easy to confuse the calculator when dividing in scientific notation, and so you may have gotten instead like 3.8 times 10 to the minus 24 molar. That would be a little bit too small in this case, and so that just has to do more with like how things are entered into the calculator. So right in this scenario, we can see that, okay, our concentration of H3O plus is on the order of 10 to the minus 9. Our concentration of OH minus is on the order of 10 to the minus 6. So this must be instead a basic solution, right? We have a higher concentration of hydroxide than we do hydronium. And so again, these two things are kind of like inversely related. In a base, you may have a higher concentration of hydroxide, whereas in an acid, you would have a higher concentration of the hydronium. Now, one way that we commonly use to represent those concentrations of hydroxide and hydronium is through what's called the pH scale. So this is used because essentially those concentration amounts tend to be really small numbers. I don't really like talking in scientific notation. I would prefer to have just like a normal number to kind of represent the same thing. And so that's what the pH scale does. So the pH of a solution is calculated by taking the negative logarithm of the concentration of hydronium So if I'm to calculate like the pH of, let's just say, neutral water has a hydronium concentration of 1.0 times 10 to the minus 7. And so the pH is equal to the negative log of that hydronium concentration, or 7.00. So right, by expressing things in terms of pH, we usually get like much nicer, cleaner numbers to work with rather than scientific notation. It's easier to type out, it's easier to see, and it also helps as just like a quick reference to kind of compare just how acidic or basic a solution may be. So let's try calculating the pH of, again, that same solution from before with a hydronium concentration of 2.6 times 10 to the minus 9 molar. So pause and use this equation to solve for the pH of this solution. Okay, so the calculation for this is very simple. I just take the minus log of 2.6 times 10 to the minus 9 molar. What I get out from that is 8.58. Just as a reminder too on significant figures when it comes to logarithms and things, when I take the log of a number, I'm going to count up the significant figures in that number. So in this case, 2.6 is 2 sig figs. The answer out is going to have that same number, but in terms of decimal places. So because I had 2 sig figs as my concentration of H3O+, my pH is going to be represented to 2 decimal places, or 8.58. Now, as I mentioned before, right, this solution, because it had a higher concentration of hydroxide and a lower concentration of hydronium, this would be a basic solution. So I also have pictured right here the pH of, some various like common household chemicals or common reagents used in the lab, right? Again, for basic solutions, these are going to have a higher pH, so a pH somewhere greater than 7. For neutral solutions, like pure water, this should have a pH equal to 7. And then for acidic solutions, we see a pH that is less than 7. And so you can see right here where certain chemicals may be more acidic or more basic. For instance, things like lemon juice and vinegar, those are known to be like acidic substances. But then stuff like ammonia, if you ever use that to like clean your windows and stuff, it's like one of the common ingredients in Windex. That's a more basic substance, and so it has then a higher pH. Let's go ahead and calculate the pH of a base instead. So here I have a strong base, sodium hydroxide, and it's like fairly concentrated. Say we have a 5.0 molar solution of sodium hydroxide. What would be the pH of that solution then? Remember that pH is the minus log of the hydronium concentration. That's not the hydroxide concentration. So think how you might connect those things. Go ahead and pause, and then we'll come back in just a moment. All right, so working through this one, trying to find the pH of this 5.0 molar sodium hydroxide solution, I found the pH to be 14.70. So walking through the steps for this, the first thing that I'm going to recognize is that, right, my concentration of sodium hydroxide, that's going to be equal to the concentration of hydroxide. Because sodium hydroxide is a strong base, it completely dissociates, and so any NaOH that we have in solution is truly just Na plus and OH minus, now separated from one another. So that's to say then that I have 5.0 molar as my concentration of hydroxide. I can then find the concentration of hydronium using again that ion product constant of water, or the autoionization constant for water, Kw. Or if I take the Kw of 1.0 times 10 to the minus 14 and I divide that by my concentration of hydroxide, then I get my concentration of hydronium as 2.0 times 10 to the minus 15 molar. And so then lastly, I can plug that right into the pH equation and say then that the pH is equal to the minus log of 2.0 times 10 to the minus 15, or 14.70 as my final answer there. Something that I want to note about this is kind of a common misconception. So it's very common for people to, see a pH scale like this one that I have on the side, and it's often represented going from 0 to 14. But that's not the limits of pH. You can have super acidic solutions that have a pH that is negative, so less than 0, or you can have very basic solutions like this one that has a pH that is greater than 14. So right, initially you may be like a little freaked out by this pH being so high, but this just tells us that we do have like a really basic solution, a really high concentration of hydroxide. Now, as kind of like a little shortcut, I will show you some other equations that we can use to calculate pH maybe even a little bit more quickly. So right, we know pH as the minus log of the hydronium concentration concentration, essentially the minus log of the H plus, so pH has to do with that. You can also, though, calculate something called pOH, which is essentially the same thing, but using the concentration of hydroxide. So pOH is defined as the minus log of OH minus. This sort of format of like P whatever equal to the minus log of whatever, we'll see this pop up in other scenarios as well. And so this is just like one of the common ones. Now, where this is really helpful is when relating pH and pOH. You can calculate them very quickly from one another as 14 equal to the pH plus the pOH of a solution. So that 14 comes again from the Kw constant itself. This is essentially the product of a bunch of like fancy log rules and things, deriving back like that Kw expression in terms of concentrations, right? We can essentially relate our concentrations of hydroxide and hydronium this way using pH and pOH. But so that's like a super helpful trick, especially if we like already have the concentration of hydroxide for a solution and we want to find the pH from it. It's just a little bit faster, and often you're less prone to make mistakes with scientific notation and things because, again, with pH, you don't have scientific notation anymore. It's much nicer that way. But so that is, again, just like a quick run through of the pH scale and how it is used. Please let me know if you have any questions, and I'm always happy to help. Bye.